So thank you all for coming. So we're here for the second talk of the afternoon. So Joe is going to continue. And this is also the last section, last presentation of the conference. So Joe, please.
Okay, so we should begin by thanking the organizer for putting together an excellent program of talks, which I, for one, very much enjoyed. So thank you, Roberto. And, you know, given that it's late on Friday afternoon and happy hour beckons, I'm going to talk for another 3.5 hours. Okay, that's not going to happen. I'm going to try and present the rest of this material succinctly so that you can arrive at the place to which you are going next. Okay, so in the last hour, we discussed convex optimization problems with random data. We showed that there was an exact formula for the probability that 0 was the unique solution for the optimization problem that we specified. And that was called Crofton's formula, which is a fact from the integral geometry of cones. And then we saw that we could simplify Crofton's formula using a new fact called the concentration of intrinsic volumes for cones. And the second hour of the talk is about why the intrinsic volumes of cones concentrate. And this turns out to be a consequence of a type of geometric fact called a Steiner formula. And we developed a new Steiner formula for cones that allowed us to demonstrate this concentration of intrinsic volumes in a very efficient way. And so my goal now is to explain the circle of ideas to you. I can't do everything in full detail, but I think that I can get across the main points, including at least a partial proof of the Steiner formula that we use, which actually turns out to be a fairly simple exercise. Okay, so what is a Steiner formula? So I think it used to be that people actually learned geometry in school. I didn't. So I had never heard of these things before I started working with these integral geometers. But it's a very simple, natural, beautiful concept. So this can be traced back to actually work of Cauchy even back in the 1820s. But the subject really started coming together with the work of Steiner around the 1840s. And he was interested in polytopes, the convex hull of a set of points in R3. And these things have been generalized massively since then. So let me give you the general setup, and I'll draw you a picture which explains everything. So we're going to let E be a compact convex set. In RD. And I'll let BJ in RJ denote the Euclidean unit ball. So Steiner formulas concern what happens when you take a set E and you inflate it. So you look at what's called the parallel body, or the expansion of the set, by adding to it some multiple of the Euclidean ball. So trying to draw the boundaries of the set E in heavy lines. And we're going to draw a tube around the edge of this set with width lambda. And this set here can be expressed as E plus lambda times the Euclidean ball of dimension D. Okay? So when lambda is 0, we just get the set E. And as lambda increases, we're adding a Euclidean ball. The set gets bigger and bigger. This is sometimes called a lambda expansion of the set. This object's also called a parallel body. You can see because when the ball isn't too big, it's flat along the lower dimensional faces of E. Okay? So the question is, how big is this object? And Steiner formulas give a very interesting answer. They say that the body of the parallel body has a volume that can be computed using an explicit expression. So you sum over all indices from 0 to D, lambda to the D minus J, times the volume of the unit ball of dimension D minus J, times a number that I'm going to call Vj of E. So, in other words, the volume of this parallel body is in fact a polynomial in the size of the expansion. There's a normalization factor that depends on the index, and that's just the size of a Euclidean ball. And the only role that the set E plays is through this quantity Vj, which is called a Euclidean intrinsic volume. And so just as we summarized cones using D plus 1 numbers, we can summarize compact convex sets using just D plus 1 numbers. And these are actually much more familiar quantities. So Vd is the Euclidean volume of A. Vd minus 1 is roughly the surface area up to scaling. V1 is proportional to the mean width. So these are all more familiar geometric quantities, and they really are measures of the content of this convex compact set E. And the interesting thing about this formula is that when you want to know the size of the parallel body, the only way that the set enters into the calculation is through these numbers, this basic geometric data. Beyond that, it is simply a polynomial in the size of the expansion. So you can see that the term where J equals D just comes from the original set itself. You don't get any more of the set when you expand. And so there is a constant term here. This is lambda to the 0 corresponding with the set itself. The linear term in this picture comes from the parts here along the one-dimensional faces. And the quadratic part comes from the corners, the zero-dimensional faces. And that's it. So the volume of the parallel body factors into the intrinsic volumes and functions of this parameter lambda. So it's a stunning fact, but the picture tells you everything. Okay. Any questions on Steiner formulas for Euclidean compacta? Okay. Now, it turns out there are also Steiner formulas for cones. So these are somewhat later. These date to the 1940s with work of Hotelling. Has anyone heard of Hotelling? What is he most famous for? Principal component analysis. Same Hotelling. Okay? So he wrote a little paper about this, which was immediately generalized by while. And there's also work by Herglot, Allendorfer, and since we're here in South America, very nice contributions due to Santalo, who was in Buenos Aires. He was sort of the dean of the School of Integral Geometers. Okay, so this is a much later theory, but it says that if you're interested in what happens when you inflate a cone, you can also write down a related expression. So here's how this works. So we're going to be interested now in a closed convex cone in RD. And we'll define K epsilon to be the angular expansion of the cone by the angle epsilon. I'm not going to define this precisely. It basically just means move away from the edge of the cone by an angle epsilon. The cone will get bigger, and the larger cone here I'm designating by the symbol K epsilon. Okay. And so the question is, can you compute the angular expansion of the cone in a similar fashion? So what's the volume of the angular expansion? Well, here when we're talking about volumes, we really want to talk about the proportion of the sphere that the cone subtends. So the solid angle of the expansion turns out to be the sum from j equals 0 to d of some coefficients I'm going to call beta jd that depend on this quantity epsilon, which is how much we've expanded the cone, and our friends, the conic intrinsic volumes of the cone. So the cone enters into this formula only through the intrinsic volumes. So we saw that it allowed us to compute the probability of intersection between a subspace and a cone in the last lecture. That was called Crofton's formula. And the Conic-Steiner formula tells you that if you're interested in how big the cone is when you inflate it, the only way the cone enters is, again, through these d+1 numbers, the conic intrinsic volumes. And there are coefficient functions here now, which are a little bit more complicated than just polynomials, but the cone plays no role. The only things that matter here are the dimension d and the index j. And in each dimension, these coefficients are fixed. They don't depend on the cone. And these are functions of epsilon. Okay? So this is a Steiner formula for the cone. I'm sorry my picture is a little bit stilted, but I hope you can see what's happening here. And it turns out that these Steiner formulas exist in much greater generality. I'm going to show you another Steiner formula in just a moment. And they allow you to connect the intrinsic volumes with metric geometry of this cone. Okay? So this is something that's defined by making the cone a little bit bigger. And you can think about this as a moment of the intrinsic volumes. It's a linear functional of this sequence with these parameters here. And so the idea is that if you could collect some moments of this sequence, you could determine the sequence, or at least determine things about the sequence. That's what we do in probability, right? We want to know something about a random variable. We collect its moments. And once we know a little bit about the moments, we can bound the probability of the random variable is large. Or we can find out what its mean is. We can find out what its variance is just by formulas of this type, linear functions of the distribution. And that's what we're going to do here to study the conic intrinsic volumes. Okay, so this paper that I wrote with my student, Michael McCoy, for which he is almost entirely responsible, resulted in a vast new family of Steiner formulas for cones. And I'll show you the general result, and we'll talk about how we can use this to understand the behavior of the intrinsic volumes. So we'll let f be a function from R2 plus, so non-negative pairs of non-negative real numbers to the reals, and this should be Borel measurable. So this is actually a little bit important. Of course, all functions are Borel measurable in real life. So, okay. Now, we're going to define a functional on closed convex cones in RD. The quantity phi of f, depending on the cone, which is given by taking the expectation of this function applied to two random variables, one of which is the magnitude, the squared magnitude of the projection of a Gaussian vector onto the cone, and the second one is the squared magnitude of the projection of a Gaussian onto the same Gaussian onto the polar cone. So I'm using the same notation as before. So G is normal with mean 0 and identity covariance, and pi k is equal to the Euclidean metric projector, just as in the last lecture. Okay. So this tells us something about the average of functions over the faces of the cone. So remember that when we project this Gaussian onto the cone, sometimes it's going to land on some kinds of faces, other times it's going to land on other types of faces, and the size of the projection roughly is going to depend on the dimension of the face we landed on. Okay? Because you project a Gaussian onto a low-dimensional space, so it looks like a Gaussian on that lower dimensional space. That's roughly the intuition here. So these numbers here reflect things about the faces of the cone and the faces of the polar cone. And we are using this function f to manipulate how we treat different dimensional factors in these two coordinates. Okay? So the theorem, which we call the master Steiner formula for cones, so result due to my student, which appears in our joint paper. And it says that there is a very nice expression for geometric functionals of this form. It says that if you want to know how big this is, you can express this by summing over all choices of dimension j from 0 up to the ambient dimension of the functional applied to a j-dimensional subspace. Subspaces, remember, are much simpler objects than cones, and multiplied by the intrinsic volumes of the cone. So every functional of this form factors into the intrinsic volumes, which contain all of the information about the cone, and some coefficients, which tell us about how the function behaves, but only through the behavior on subspaces. And the great thing is that these things are usually not so hard to calculate. So it doesn't matter because of the rotational invariance of the Gaussian. Yeah. And equivalently, so what happens when you project a Gaussian onto a j-dimensional subspace? You really do get a Gaussian of j dimensions. And then when you take it square normed, you get a chi-square variable with j degrees of freedom. Now, the polar of the subspace is the orthogonal complement, so it's got d minus j dimensions. And the projection of the Gaussian onto that orthogonal complement is independent from the Gaussian on the subspace L. So the part of the Gaussian in L and the part of the Gaussian and its orthogonal complement are two independent Gaussians. This guy has squared norm distributed like a chi-square variable with d minus j degrees of freedom, but it's independent from this one. And so what that tells you is that you could also write this formula in the following fashion. So phi k, phi f of k, is also equal to the sum from j equals 0 to d of the expectation of the function f evaluated at a chi-square with j degrees of freedom and a chi-square with d minus j degrees of freedom that is independent from the first one, and multiplied by the intrinsic volumes. So these are independent chi-square with j degrees of freedom. So this is actually a very, very actionable formula for functionals of this form, and it allows us to understand the intrinsic volume sequences by computing functionals like this. So you could think about going either direction. If you want to understand these functionals, you could do that in terms of the intrinsic volumes. We're going to go the other direction. We're going to understand the intrinsic volumes by using this formula with functions where we can determine this completely. Okay. So, any questions about the statement? Okay, probably the question you should be asking is, why is this a Steiner formula? So, it turns out you can actually prove this result is a consequence of the master Steiner formula. I'm not going to do that for you because it's a little bit messy. I'm going to prove instead what is called the Gaussian Steiner formula, which treats a Euclidean expansion of a cone. So here's how this works. So the proposition that I'm going to use to demonstrate that this is a Steiner formula is called the Gaussian Steiner formula for cones. And it says that the Gaussian measure of the parallel body of the cone, so we're going to expand this cone by an amount lambda in every direction. And this is defined rigorously as the squared distance from g to the cone being less than lambda, okay, where again, g is the same standard normal variable, that vector that we've been using everywhere. So the Gaussian Steiner formula says that we can compute probabilities like this, the measures of these sets, in terms of the intrinsic volumes and with coefficients that are simply the complement of the distribution function. Actually, this is the distribution function of a chi-square variable. It's a distance squared. Actually, you're probably right. It should be the distance. Yep, you're right. Uh-oh. Have I... Let's put a square here, and sorry, let's I'm pretty sure I want a lambda here, so maybe I need a lambda half here. Okay. Good point. Okay. So in other words, we're in a picture that's similar to the one that I'm erasing, and which I'm going to replace by the corresponding result, or the corresponding picture. So for a cone K, we're going to look at the parallel body. So this is K plus lambda 1/2 of the unit ball. Okay, so we're going to be looking at this set here, which is the cone inflated in every direction. And we're going to write down a formula for the probability that a Gaussian lies in this parallel set of the cone, its expansion by root lambda. And it says that to determine this, all we need are the intrinsic volumes and the distribution functions of some chi-square variables. And notice the only place the cone plays a role is here through the intrinsic volumes. So we factor this into a function of lambda, the size of the expansion, and some information about the cone. Okay, so let's prove this. So we're going to consider a function f here in our Steiner formula, which is very simple. It should be 1 when b is less than or equal to lambda, and 0 otherwise. Okay? That's certainly Borel measurable, function of two variables. And now we can make the following calculation. So the probability that the squared distance from G to the cone is less than or equal to lambda is equivalent to the probability that the projection of the Gaussian onto the polar cone is less than or equal to lambda. And so this is based on standard facts about orthogonality, because cones, convex cones, introduce an orthogonal decomposition of the space. So for any point, you can write it as its projection onto the cone plus its projection onto the polar cone, and those two projections are orthogonal to each other. Okay? So this is a simple fact from Euclidean convex geometry. And applying the Steiner formula, we find out that this is the sum from j equals 0 to d of the expectation of our function f at xj and x d minus j prime times the intrinsic volumes of the cone. So remember that the second variable is the one concerned with k-polar. And so this really is just the expectation of the indicator that the second variable, which is to say the projection onto the polar, squared is smaller than lambda. We apply the Steiner formula, we get this expression. And then we remember that, again, the function has this form, and it tells us that this expectation is just the probability of x d minus j prime being less than lambda. again, times the intrinsic volumes. That's it. So once you have a formula of this type, you can produce all sorts of Steiner formulas. So this Gaussian Steiner formula appears in work of Jonathan Taylor, and it probably goes farther back than that. But this is a very simple proof of this type of fact. And it tells you that even though this formula looks kind of abstract here, it really does contain information about expansions as sets, which is the kind of thing that you hope a Steiner formula is going to do for you. OK. Now, any other questions on this before we move forward? OK, so this is a Steiner formula. Now, the reason that we are interested in this Steiner formula is because we want to understand how these intrinsic volumes behave. And we're going to do that using probabilistic analysis, and we're going to use the Steiner formula to translate in between properties of the sequence of intrinsic volumes and these geometric functionals. So to start out, the first observation I'm going to make is that there is actually a metric formulation for the statistical dimension. So, as I said before, the statistical dimension is this complicated thing, right? It's the mean value of the intrinsic volume sequence. We don't know how to compute intrinsic volumes. So that's a problem. But it turns out that this gives us a very effective tool for actually computing that quantity. So the statistical dimension of a closed convex cone K is given by the expectation of the norm of the projection of a Gaussian onto the cone in squared Euclidean norm. So even though we defined the statistical dimension in terms of these intrinsic volumes, in fact, it has a metric characterization. If you want to compute it, all you need to do is take a Gaussian, project it onto the cone, and figure out how big it is on average. And in fact, this formula is pretty useful. You can do this in a lot of cases. And most of the situations where we know how to compute statistical dimensions rely on this identity. Although there are some situations where you actually really do need to use considerations from the theory of intrinsic volumes, and the metric approach doesn't help. So how do we prove this? OK, we're going to look at a different function. Let f of a be a. Very complicated function. I think it's Borel measurable on non-negative pairs. And when we apply the Master-Steiner formula with this function, here's what we get. I'm going to go backward. It's a little bit clearer, maybe. So this is phi of f. And the Master-Steiner formula tells us that this is a sum from j equals 0 to d of the expectation of xj, where this is a chi-square with j degrees of freedom, times the intrinsic volumes of the cone K. Now, what's the expectation of a chi-square with j degrees of freedom? It's j. So this really is just the mean value of the sequence of intrinsic volumes, which we gave a name, and that was the statistical dimension. So again, this allows us to translate properties of the intrinsic volumes into metric properties of the cone. And in particular, this result allows us to compute statistical dimensions by doing Gaussian analysis. It is an extremely powerful tool. Now, as I said before, the reason that the I'm actually going to keep this. Okay, so the reason the statistical dimension was an interesting parameter was, in large part, because the intrinsic volumes concentrate at that point. And I'd like to explain quickly why that is, and then if we have a few more minutes after that, I'll tell you a little bit about why the Steiner formula holds. So we're going to introduce a random variable associated with the cone, which takes the value j with probability vj of k. So this is called the intrinsic volume random variable. Okay, so for a given cone k, we take its sequence of intrinsic volumes, and we make a random variable that has value j with probability vj. Okay, and we're going to use probabilistic methods now to understand the sequence of intrinsic volumes. As I said before, you should think about this as a moment of this random variable vk. So here we saw that this is really the first moment of the sequence. You can look at the second moment, which is the variance. So in that case, you'd have a j squared here. Other things like that. We're going to go in a slightly different direction because I want to show you that the intrinsic volumes concentrate. So here's a proposition. For all real eta, the expectation of e to the eta times this intrinsic volume random variable is equal to the expectation of e to the xi times the projection of a Gaussian onto the cone squared with a different parameter xi, where xi is related to eta by the formula 1/2 1 minus e to the minus 2 eta. So this is always less than 1/2. So it establishes a bijection between r and the set of numbers smaller than 1/2. Okay, so remember, when you want to prove concentration inequalities, what do? You look at exponential moments and you apply the Bernstein trick. And that's what we're going to do here. We're going to compute exponential moments of the intrinsic volume random variable by passing to a Gaussian random variable. We're going to use this formula to get bounds on the moment generating function of vk, and then we're going to pass back to a concentration result for vk, which will tell us that, in fact, vk concentrates. The conic intrinsic volumes are always close to their mean. Okay, so first of all, let's prove this result. We set f of ab to be e to the xi a. That's it. That's the whole proof. After that, it's just like this argument. Plug everything in here, and this is what you get after you compute the moments of the chi-square variable. Okay? So this follows immediately from this choice, and the standard formulas for the moment generating function of a chi-square. Okay, great. So let's see how the rest of this goes. I'm not going to go through all of the details because from some point of view, they're routine and they're also kind of involved. So the second step is to understand how well this guy concentrates. But this is just a function of a Gaussian variable, and it's a pretty nice one at that. Okay? Because these projections are always contractions, and so these things are, if you're without the square anyway, is a Lipschitz function. So you can see that this thing is going to concentrate. You can write down estimates for the moment generating function. And so the way this works is that if you look at moment generating function of this quantity squared minus the statistical dimension of the cone, which is exactly the mean of this, as we just saw. This is bounded by the exponential of 2xc squared times the statistical dimension of the cone divided by 1 minus 2xc. So this is a relatively standard form for a moment generating function, and it leads to Bennett-type inequalities. And this follows using log Sobolev inequalities. Okay, now once you have this and that, it follows that the moment generating function of the intrinsic volume random variable minus its mean satisfies a beautiful inequality. So the moment generating function of this guy is controlled by e to the 2 eta minus 2 eta minus 1 divided by 2 times the statistical dimension. So again, this is the kind of thing that shows up when you prove Bennett inequalities for sums of independent variables. And this guy here is effectively the variance.
So I guess you could switch between cone and the polar cone.
Yeah, at that point. Yeah, you get sharper results if you do that.
Yeah, which is the value you gave in the first part.
That's right.
What I gathered.
Absolutely. Absolutely. So you do the same thing with the polar cone, and you get a second set of bounds, and they're better. But I'm going to leave that out because I want to tell you about the formula quickly before we wrap up. And what this tells you is that the probability, once you apply the Bernstein method, the probability that the intrinsic volume random variable is close to its mean, or more precisely, the probability that it exhibits a large deviation from its mean, is bounded by the exponential of minus lambda squared over 4 over delta k plus lambda divided by 3. And you could also get a delta k polar here if you repeated the argument mutatis mutandis. Okay? So this tells you exactly what I said before, that the intrinsic volumes concentrate around their statistical dimension. And the width of the lobe here is on the order of the square root of the statistical dimension. In fact, it's even smaller than that if this distribution is skewed toward the right instead. Is closer to, the mean is closer to D. Okay. Any questions about this? I realize that that was kind of a roller coaster. But the simple fact is that if we can get estimates for the moment generating function of this guy, we get concentration inequalities. To do so, we use the Steiner formula to pass to a geometric random variable, just the projection of a Gaussian onto the cone. And that's something that we can study using classical tools. So this, when centered, so remember the mean of this is the statistical dimension. When you center this random variable, its moment generating function is bounded. This follows from log Sobolev inequalities, which are a classical method for producing concentration. And then when you combine this result with this, and you apply the Bernstein trick, well, okay. Combining these two results, you get a bound for the moment generating function of the intrinsic volume variable. Then apply the Bernstein trick to get the concentration inequality. And that gives you exactly the picture that I drew on the board before. All right. Great. So now I'd like to explain briefly the ingredients in the Master-Steiner formula. Proving this whole thing for Borel measurable functions actually turns out to be quite a lot of work because you have to make several approximation arguments along the way. But if you want the most basic form, which already contains all the geometric intuition, it's quite simple. So what we're going to do is restrict to the case where K is a polyhedral cone. And I'm also going to assume that the function is bounded and continuous. Though we'll come to that in a minute. Okay. So, few facts. So for each face f of K, the outward normals to that face compose a face, a unique face, and f of the polar cone. So I'm just giving this guy a name. So if you look at everything that's normal to a face, it makes up another face of the polar cone. So there's an anti-isomorphism between the faces of the cone and the faces of the polar cone. Okay. Now, there's a fact which is effectively due to McMullen in 1975 for a very influential paper on integral geometry that says that you can tile all of RD as a disjoint union over all of the faces of the cone so for each point in each face of the cone, you fibrate it with the normal face. Which is orthogonal. So when you do this for every point in every face of the cone, those fibers fill out all of RD. These points and these points are orthogonal to each other. So there's an orthogonal decomposition of everything in RD. And furthermore, there is no overlap. All right, because every point in the cone belongs to the relative interior of a unique face. Okay, there's a picture that I'm not competent to draw. And the second fact that you need is essentially another definition of intrinsic volumes, which is that the intrinsic volume J is the sum over faces of K with dimension J. And on that face, you multiply the solid angle of the face with the solid angle of the normal face and add them up. This kind of makes sense from the definition of the intrinsic volumes because the jth one is telling you about all the stuff that's closest to a j-dimensional face of the cone. So we add up the amount of space that's closest to one of those faces of dimension j. That's it. So this is an alternative way of looking at that formula that I described before in terms of projections of a Gaussian lying in the relative interior of a j-dimensional face. So this is the amount of space that projects onto a specific face of dimension j, and you add that up over all of the possible faces of dimension j. Okay. Now, with this, we can give a sketch for the important case, which is the one where K is polyhedral and F is bounded and continuous. Okay. So I'm going to define variables U to be the projection of a Gaussian onto the cone, and V to be the projection of the same Gaussian onto the polar cone. So these are orthogonal to each other, and so they're independent, roughly. Now, we'll write down what it is we need to calculate. So phi f evaluated at the cone is equal to the expectation of f of the norm of u squared. Oh, I think I like w's better here for the reason that v's are intrinsic volumes. Okay, so this is what the definition of this functional phi f. And now we're just going to split space into j-dimensional faces. Okay, so we're going to sum over all possible dimensions of a face, and now we're going to sum over all faces of K with dimension j. Okay, and we can express this as the same function restricted to the relative interior of the face, and we're going to force u to be in that particular location. So we're taking this integral, we are splitting it up depending on where u is. So if u projects onto a specific face, we're going to break that piece out. And then we're going to add up over all of the faces with dimension j, and we're going to add up over all possible dimensions for those faces. So this is because the u's are already projected onto the cone. It's everything. Okay, and it's clear that each point G projects to a unique point in the relative interior of some face. So this uniquely determines faces. All right. Now, let's look at this quantity here. Star of f. So star of f is just a Gaussian integral. So, you know, the Gaussian measure has got this normalization factor, and we've got the integral over the relative interior of the face because we're restricting to that location. We've got the integral now over the normal face, which corresponds to the stuff in W, because u and W have to be orthogonal to each other, because they're projections onto a cone and a polar cone. And we've got the function of the two variables x and y, x in the relative interior of the face, y in the normal face, and with the Gaussian density here, sitting up top. So we're just rewriting this expectation as an integral. Okay, now what do we do? So whenever you see something like this in the integrand, you change the polar coordinates. Okay. And when you do that, you wind up with something that looks like the solid angle of f times the solid angle of the normal face times some really complicated function that depends on f. It depends on j, because we're looking at j-dimensional faces, and it depends on the ambient dimension d. So effectively, I'm integrating over the intersection of f in the unit sphere. That's spitting out a solid angle associated with this face. I'm integrating over the normal face intersected with the unit sphere. That spits out the solid angle of the normal face, and then I collect everything else in this function. All right, almost done. So I've already used this, so I can erase it. So now we just take our calculation of star f and we plug it back in here. And we obtain the sum from J equals 0 to D, the sum over all these faces. And we computed this integral to be the product of these two solid angles times this function IF. This is the jth intrinsic volume. And we wind up with an expression that's almost of the type that we need. Okay. Now, what's the problem here? I promised you that the coefficients here are these simple guys that we obtain by sticking a subspace into the functional phi f, this geometric functional. Unfortunately, I have this horrendous integral that I don't know very much about. So how am I going to deal with that? Well, there's some things that we know the intrinsic volumes of already, like subspaces. So I'm just going to plug a subspace into my formula and see what happens. So let's apply the formula to a subspace Lk of dimension k. That'll give me phi f of Lk is equal to the sum from j equals 0 to d of if jd times vj of Lk. What's this? This is a Kronecker delta. It's the equal to 1 only if j equals k. So this collapses to if of jd. That's it. So this proof is really just a decomposition of the space into the faces of the cone, the observation that the faces and the normal faces allow us to split the Gaussian into two independent parts, conversion to polar coordinates, and then combination of the solid angles back together into the intrinsic volume functionals.
You really need that process of how you get those solid angles type something that does not depend at all on the moment.
That's right. That's right.
I guess it should be obvious once you.
Well, the solid angles do depend on the cone, right? I mean, that's where the intrinsic volumes come from.
But it's not entirely.
It's not entirely clear that IF doesn't depend on the cone. Well, I mean, the thing is that IF doesn't have any cone in it. All of the cone is here, and this stuff is, winds up in IF. And so you can see that maybe the dimensions make a difference, but it's true. You have to write it out just so to convince yourself. But and then to get from here to the rest of the way, you approximate polyhedral cones by, general cones by polyhedral cones, and then after that, you have to check the continuous continuity of the intrinsic volumes, and then after that, you need to do some integration theory to pass from bounded continuous functions to non-negative Borel functions, and then you need a condition to make sure it works for other things. So there are a bunch more steps to get this in generality, but the idea is on this one panel. Okay. Thank you so much for your attention. That's it.